All right, so now that we are kind of experienced with the Bayesian philosophy, Bayesian approach, we're going to apply that to the whole development of conditional probability models we did last week. All right, so we want to do Bayesian conditional probability models. That'll have some interesting benefits for us in terms of being able to express kind of our uncertainty in the predictions in our predictive model. So let's do a quick recap from last week. The parts that are most relevant for this conditional probability modeling. So in the terminology this week, we have a parametric family of conditional densities. So instead of just py theta, now it's py given x and theta. X is the input, y is the outcome space, and these are the objects that we want to produce. We want to produce distributions on y. That's our action space. So whereas before we were calling y as an element of the sample space, now to align with our terminology from conditional probability modeling, we'll call y the outcome space and x the input space. Okay. Theta is still a parameter, now parameterizing this set of conditional distributions. With conditioning, by conditional we mean conditioned on x. All right. Great. Just as before, density functions can be replaced by mass functions throughout. All right. So as before, one way to think about these things is that we have a set of densities that describe the world we observe. And one of those is correct. We just don't know which one. So the question is what theta is the right one, and how do we get by if we only have data sampled from this distribution? But here, sampling some data is not quite as obvious what we mean in this case as it was in the previous case. And the reason is that, what about the x's? This distribution tells us quite clearly for given theta and an x, how do we sample y? But what about x's? All right. So in statistical learning theory, we assumed we had this joint distribution on x and y. And we can still assume that here, but we do not need to, at least to get the results that we're going for. So what we're going to do, what we're able to do, is assume that we have n inputs, x1 through xm, and they can be chosen any way we want. Throughout our development, assume that the x's are fixed and that they are known. And so if you want, you could think of every statement we make as being conditional on the x's. But the point is that we don't need a probability model on the x's. All right. So for any input xi, we observe a yi sampled randomly from the conditional distribution of y given xi, theta, for some theta that we don't know. All right. So we're going to assume the outcomes y1 through yn are independent once we know the x's. So we assume we know the x's, they're independent. All right. Any questions on the setup here? So let's move into it a bit. Let's write down let's kind of adapt our likelihood function here. So we have our data d. I'm just going to write the y's in the data for d, since that's the only kind of random interesting part. The x's we assume are fixed and known and shared, and we can assume we always have those. So I put them in the conditioning part here. We could have just as easily left them out. So the conditional density, or likelihood, of the observed data d, given the inputs and theta. This is our factorization because of the independence assumption. And just as before, if we want to highlight the fact that for fixed data, this thing is a function of theta, a function of the parameter, we can introduce this notation for the likelihood function. All right. And of course, we can then still define our maximum likelihood estimator as the argmax of that likelihood function for the given data. Very straightforward adaptation. All right. Let's recap. I believe we did this example last week, the Gaussian linear regression case. So let's instantiate that in our new terminology. So we have a conditional probability density family where y given x and w, x is RD, and y is living in reals. And so our model is that the mean of w given x is w transpose x, right? So that's a linear function of the input x. Very easy. We're going to assume that sigma squared is known. So the true model is for some w that I don't know, we get an input x, we do a linear transform, w transpose x, for some w we don't know, and then we have some Gaussian noise with variance sigma squared that we add to it. And that gives us y. That's how y gets generated from x. And so we'd only need to know w to know how everything works. So what's our parameter space then? W is our parameter. What space does w live in?
RD.
RD, exactly, right. All right. Here's our data. And we're assuming the conditional independence. And so we can write down the likelihood. So yi given xi w is, what's that? That's a mathematical expression. What would I need to write down there if I wanted to write this out? Some density for a Gaussian, right? OK. So
e to the power negative.
Thank you. E to the power. This is the key piece.
Y minus W transpose.
There you go. That's right. Y minus?
WXI.
Yeah, yi minus W transpose xi.
Take the square.
Great. And then?
Divided by 2 sigma squared.
Great. Thank you. OK. All right. So this is our likelihood. What's it a function of? W, yes. We're considering xi and yi to be fixed, and xi is always fixed and known. We're assuming we've observed the data d, so yi's are all fixed and known. We put that in the subscript. And the dependency we're still interested in is w. Great. And we went through last time that you should be able to see in your head what a simpler expression is for the maximizer of this likelihood, right? If you want to maximize this likelihood, how can we rewrite that much more simply? Yeah, you could take a log, break this up. We're trying to maximize over w. The sigma piece doesn't matter. Just like we worked through last time, it comes out to just minimizing this least squares, solving this least squares problem. OK. Great. All right, so that was our development of Gaussian linear probability models. So let's go Bayesian on this. All right, so we have our conditional density piece. And we're going to add in this new piece, the prior distribution. I went generic again, so there's not w. We're back to theta as our parameter space. So we have a prior distribution. And we'll be looking for the posterior distribution. We can, as usual, factorize this, rewrite this by Bayes' rule into likelihood piece times prior. Posterior is proportional to likelihood times prior. And the likelihood piece, we're assuming for fixed data, we like to write it this way in terms of a likelihood function, LD theta. The likelihood function we just calculated, right? That was this. This is the likelihood. So we plug this expression into for LD theta, and we need to choose a prior. Well, this is if we were doing Gaussian, we would plug that in. Okay. But this is still generic. All right. So now in the Gaussian case, let's choose a Gaussian prior distribution. Why do you think I'm choosing a Gaussian prior? Because it's a conjugate family. That's right. It's a conjugate family. So let's take the prior on W, so we're back in this case, to be zero mean Gaussian with some covariance matrix sigma 0. All right. You guys know this terminology, SPD, symmetric positive definite? Covariance matrices must be symmetric and positive definite. So just requiring it be a covariance matrix. The posterior distribution is proportional to likelihood times prior. And we plug in this expression for the likelihood, which we derived over here. And then we write in the density for the prior, which is just, if you don't remember the multivariate Gaussian density, I guess you could look it up, and write that in. So that's our posterior. It's proportional to that. What space does this live in? What space is this a distribution on? RD, right. So if you wanted to plot this like we had before, D better be 2 or maybe 3 at best. But you could look at it, visualize it. OK. So there's one more fun thing we can do when we have these conditional probability models and a posterior and these distributions on theta. So for a given theta, oh, your question?
You haven't translated that back into a Gaussian.
Oh, did I make a mistake here?
No. What I mean is theoretically, then this would be represented in another Gaussian because that's compared family. What is that?
Great question. So I claimed that the Gaussian is a conjugate prior, and which means that this, as the posterior, better evaluate to Gaussian as well. And so this mess better simplified to something simply, which would be basically a mean vector and a covariance matrix. So your question amounts to, if you're not lying to us, then this should correspond to a Gaussian density for a particular mean and a particular covariance. And we will write that down later. Great point. All right. So we have these conditional densities. For any theta, for any fixed theta, what this does is we get py given x and theta. So for fixed theta, this gives us, for any x, a distribution on y. So that's basically the prediction function, the form of the prediction function that we were working with last week, right? We get an input x, we produce a distribution on y. That's what py given x theta is. Once we fix theta, we have each one of these things. For any theta, each one of these things is a prediction function. So we could think of this as a hypothesis space indexed by theta. All right. OK. That's interesting. Now, in Bayesian, we have these other objects which are distributions on theta. They come in two flavors so far, the prior distribution and the posterior distribution. So let's catch up here. So we have these two different types of distributions on theta. And what this amounts to is a distribution on prediction functions, because every theta corresponds to a prediction function that gives, and a prediction function here, for any input x, we get a distribution on y. All right? So we have a distribution on theta, which induces a distribution on prediction functions. Distribution on prediction functions. What could that give us? Well, for example, suppose you have a distribution. Suppose you have your prior distribution on theta. We haven't seen any data yet. But you have a prior distribution on theta. And someone says, hey, I got an x. I need a prediction for y. I need a distribution on y. What do you got? And I haven't seen any data yet. OK, but still, you have to tell me a prediction for y. OK, so I'm going to use my prior distribution on theta. That gives me a distribution on prediction functions. Each one of those prediction functions gives me a predicted distribution for y. I can average them together according to my prior distribution. And that gives me a single distribution on y. That distribution is called a predictive distribution for y. We're going to come back to this because I think it'll be more clear when we get to an example what's going on here.
So there is like a third distribution. So we have p of theta, we have posterior, and then we have a distribution on y.
We have so a lot of distributions floating around in Bayesian statistics. So we have a prior on theta, a posterior on theta. Both of those are distributions on theta. and we have a distribution on y given x for each theta. And what I'm calling a predictive distribution is a distribution on y given x no theta. What is it? We integrate out times, this would be with respect to the prior. So if I don't have any data yet, someone needs a predicted distribution for y given x. What are we going to do? OK, well, let's integrate out over theta, which we don't know, with respect to our prior. And we get a single distribution on y given x. If we had some data, we would just integrate out on the posterior distribution of theta, called a predictive distribution. Let's not do any more work. Let's look at the results of an example. All right. So the setup here is we have some input space. I restricted -1, 1, doesn't matter. Output space is reals. And here's the model of the world. Given an input x, we get some kind of a linear combination, not linear, we get an affine function of x plus some noise epsilon. Epsilon has 0 mean and a little variance. All right? So here's x, here's y. There's some true w0 and w1 that we don't know. But let's suppose it could look like this. All right? And somehow someone chooses some x's for us, or we choose them ourselves, or they're random. It doesn't matter. And then the world generates these sample points. y1, y2, y3, y4, y5. All right? That is a sample draw from this. All right. And we'd like to know the w0 and the w1 corresponding to that line. OK. So another way to write it is y conditional on x is Gaussian with mean the affine transformation of x, and then a little bit of variance around that. All right, so what's the parameter space here? Yeah, R2, great. So I could draw it, because it's R2. We could say, oh, maybe this is W0 and this is W1. And as we've done many times before, any point in this parameter space corresponds to a different line in this prediction space, right? OK. All right. All right, and we want to be Bayesian here, so we're going to put a prior, Gaussian for convenience, on W0, W1. So this is a two-dimensional Gaussian distribution on this space. This is a parameter space. So there's someone put some Gaussian distribution. I'm drawing contours here. Right. Gaussian distribution. All right. So we've run some simulations. Well, these are taken from Bishop's book, but some simulations were run. So on the left, we have a contour plot of our prior distribution. It's 0 mean and circularly symmetric because that's a scaled identity covariance matrix. This is our parameter space. On the right, what we've done is we've sampled several points from the prior distribution. And every point here gives us a W0, W1, which corresponds to a line by f of, let's say, W0 plus W1 x is this line. Okay. So each of these lines corresponds to a random draw from this distribution, the prior distribution. So now we observe one point. It shows up in this space because this is the observation space, input and output. And having observed one point, we can update our posterior distribution using the formulas that we wrote down but didn't simplify. And that looks like this. This plus here, we've just overlaid the actual correct parameter values. All right. All right. Is this clear what's happening here? Add more data. So here's after 2 observations. Oh, one more thing I didn't say. So here's our updated posterior. And then we've drawn new W0, W1s from this posterior, and those correspond to these lines here. And the idea is that each of these lines will converge to something that's more close to the true W0, W1 line. All right. Here's after true observations. Here's after 20 observations. And you can see that the red lines are really converging. The W0, W1 are really converging. The posterior distribution on the parameter space is kind of getting smaller and smaller variance. And that corresponds to the prediction functions getting closer and closer to each other. All right. Is that clear? All right. So the closed form for the posterior distribution. So I'm just going to write it down here, but we have some notes that are posted that work through the details. We could maybe after this lecture if there's time. All right. So for convenience, we're going to use our usual design matrix, which has the examples as rows. And the posterior distribution for W, given the data D, is Gaussian as promised. And here's the closed form that we're looking for. So let's start with the mean vector. Does it look familiar? So this looks a lot like the solution to ridge regression, L2 regularized square loss minimization. And we'll make the correspondence precise in a minute. OK. This piece, this variance piece, we're going to dig into that a little bit more in a second. OK. But the interpretation is that this posterior distribution, sigma p, is kind of a measure of the uncertainty in our knowledge of W, our posterior knowledge of what W is, what the best line is. So we hope that as we get more and more x's, this matrix gets, in some sense, smaller. So the covariance matrix, in some sense, gets smaller. So you could think of that in terms of its eigenvalues or determinant, or different ways to assess kind of how big this covariance matrix is. All right. OK. So if this is the posterior distribution, just as a quick concept check, what would be the map? So suppose we wanted a point estimator for W, for the unknown W. We have the posterior distribution, full closed form, very nice. What would be the posterior mean, first of all? Yeah, the posterior mean is the mean of the posterior distribution, which we know for Gaussian is the mean parameter, which is this expression. OK, so posterior mean is that. What about posterior mode, or the map?
It's all the same.
The same. That's right. Gaussian distributions, the mode and the mean are the same. So the map and the mean are both mu p. Great. All right. Now the correspondence to ridge regression. If we had chosen our prior distribution, our sigma 0, to be this sigma squared over lambda I, well, what's lambda? We just introduced lambda there. Then we get this as the posterior mean and posterior mode, which is a spot-on exact match for the solution for least squares ridge regression. All right, let's dwell on this match for a moment. So how does this help us link the notion of a prior distribution to a notion of an L2 regularization? What's the connection? Suppose so lambda is the regularization parameter from L2 regularization. So if lambda is very large, so a large lambda, that means we're regularizing very heavily. We're shrinking. We're really preferring W to be close to 0. That's what L2 regularization does. It penalizes deviations from 0 very heavily. So if lambda is large, what does that say about the corresponding prior covariance? Right? Because there's an exact correspondence between the prior we put on, if it's of this form, sigma squared over lambda, the prior we put on W and the solution, the posterior mean.
very certain.
Say again?
This is very
Very certain variance is small.
Great, great. So if lambda is very large, so heavy regularization, that corresponds to a very small variance, because lambda in the denominator, it shrinks those kind of diagonal elements of the covariance. So a large lambda corresponds to a rather certain prior, a low variance prior, a prior concentrated very closely around what? What is our prior concentrating on? 0, right. So our prior is saying if lambda is large, so equivalent to a lot of algebraic regularization, that's equivalent to having a prior on W, a prior belief on W, centered at 0 with very, very small variance. All right, what about the other direction? As lambda goes towards 0, so we get further and further from lighter and lighter regularization, corresponds to a prior that's more and more diffuse, more and more spread out on RD. All right. Great. Now I want to tie it to some statistics that you might have seen before for the Gaussian linear model. This is mostly of interest if you have seen it before, but maybe we can fill in some background that we can all get something out of this. So in traditional regression, if you're in a statistics class and we talked about ordinary least squares estimator for regression, we would say it's a random variable. Why would we say it's random? So the OLS or MLE estimator for W0 and W1. It's random because in this context we're considering the sample random, right? In that sense it's random. And in that sense, if we consider the data random, the estimator W hat, say, the least squares estimator, is itself random, and so it has a distribution. And it'll have a mean, and it'll have a variance, and all those things. And you can compute those. So if we assume we have the observations are just as we had before, our W transpose X plus some Gaussian noise, then the distribution of the OLS estimator W hat is Gaussian, and the mean is W, which is what we want. So it's nice. It has expected value equal to what it is trying to estimate. That's a nice property for a point estimator. That's good, unbiasedness. And the covariance of W hat has this form. So the interpretation there is we have some data generating distribution. We take a draw from it. We estimate W with a W hat. If we took another draw from it, we get another W hat. And if we keep drawing from that, each of these draws is a draw from a Gaussian distribution with mean W and this covariance matrix, this covariance. All right. So how does this compare with the variance matrix of the posterior distribution? Remember, the posterior distribution also was Gaussian. For the covariance part, we have two things. We have the covariance of the posterior distribution, and I wanted to make a comparison to the covariance that we get from traditional statistics for the estimator. And you kind of see they're very similar, right? So this term matches exactly, but now we're adding a piece. Sigma 0, what was that? The covariance of the prior distribution. Let's do a little bit of kind of units analysis. So imagine everything were one-dimensional for simplicity. If sigma 0 gets very large, that's a diffuse prior, a very uncertain prior. Sigma 0 inverse gets small, very small, which makes this expression very close to this, which means this and this are very close. So when sigma 0 is spread out, very large, very, very unconfident prior, these two covariances are very similar. If we have a very confident prior, so sigma 0 is very small, then these are quite different. Is this in some sense smaller or larger? Let's see. If sigma 0 is very small, this thing is large. The inverse of it is large. which means the inverse of the full expression is small again. So when we have a very tight prior, that gives us a tight posterior. All right. OK. So great. So that kind of justifies this terminology that of informativeness in the prior. So if we have a prior that's very concentrated, that's kind of called an informative prior because it has a lot of influence on your posterior. It pulls you away from what you would get if you only looked at the data. So before we were saying that the posterior mean has this exact match to the regularized, kind of L2 regularized least squares solution. Now let's look at the full posterior density. And as though we're finding the map solution, this is really just the same thing again. It's just pointing out that the objective function that we're solving also has connections directly to the ridge regression objective function, where this is the loss piece for ridge regression, but it corresponds to the log likelihood for our development here. And the regularization piece corresponds to the log of the prior distribution. So it's kind of making, before we made the connection at the solution level, like we said, oh, the solutions are exactly the same. And now we're going back one step and connecting the objective functions, the thing we're minimizing to get the map solution, and recognizing the parts that match to the objective function for ridge regression. All right. Any questions? OK, and now we come to predictive distribution again. And so this is about, given a new input point x, how do we come up with a distribution on y? So we can just work our Bayes rule. So we don't want to have to choose a particular w. Choosing a w and plugging it in would be kind of our frequentist approach. We get a point estimator for w, and then make predictions based on that. But in Bayesian statistics, we don't want to do that. We want to average over our posterior belief about w. So here we condition on w and then integrate out with respect to the distribution on w, the posterior distribution on w. OK. The data becomes irrelevant once we condition on w. So it simplifies a bit. OK. And then for Gaussian regression, we could do this and come up with a predictive distribution. And it looks like this. So for a new data point x, what's the distribution on y? Again, it's Gaussian with a particular mean and variance. Sigma nu should be what type of object? Just to make sure we're in the right space. Scalar matrix? Scalar, because let's assume x nu is a single input. We want a distribution on reals. Sigma nu is a number. So what's going on here? So the mean of the predicted distribution is the mean of the posterior distribution for the parameter, and we apply that to the input. And the variance has a nice decomposition, which is interesting. So I have two pieces. One is sigma squared. So all of our data is generated by taking the true w and going w transpose x and then adding some Gaussian noise with variance sigma squared. Right? So the predictive distribution for y has to account for the variance that's inherent in the data. So that's the sigma squared piece. So this is decomposing the new predictive variance into the two pieces. There's the inherent variance in y. And then there's this other piece, which is interesting. This is from the variance in w. So if we had w exact, this wouldn't be here, right? But there's uncertainty in w, and that adds to our uncertainty in the prediction of sigma. questions on that?
We're summing over a p, or all p's, or what are we summing for all data points? Or something?
Oh, wait, where's there a sum?
Yeah, Earl, in the from variance to W last line.
Oh, that's not a sum. Sorry. That's sigma sub p. That's the posterior variance of our distribution. So W, we have a posterior distribution on W after seeing some data. It has a mean and a variance. And that's the variance of W, right? Sorry about that. Yeah. Anything else to say about this? Maybe not. Let's look at a picture. Once you could do something like this, you can make these sorts of predictive plots with error bands. So these are, for each x, we can, what did we call it?
Confidence.
Well, the credible set. This is the Bayesian version of confidence interval, or prediction interval. And this would capture, this range would capture the two sources of uncertainty, the inherent uncertainty in the data, the noise in y given x, and the noise, the uncertainty in our estimate of w of this line.